So in this video, let's talk about how do we find the enthalpy of vaporization or the heat of vaporization, whichever phrase you want to use. Um, so we can find it experimentally, which is the useful thing. So if we're able to take a sample and measure its pressure or its vapor pressure specifically at different temperatures, we can plot the natural log of pressure versus the inverse of the temperature in Kelvin. And we should get a plot with a negative slope like this. Yeah. And and from this, the slope of this line would be equal to the negative of the enthalpy of vaporization divided by R. R is one of those constant values that we use a lot. In this case, it has it's a lot of different numeric values based on its units. We're going to use the version that's 8.134 joules per mole Kelvin. So once we have this information, we could then take the slope and calculate just that enthalpy of vaporization from the slope of the line. And so this would involve taking the pressure and temperature values for a substance as you increase or decrease temperature to get a number of points and plotting them, and then finding the equation of the best fit line to those points, and then taking the slope and multiplying it by negative R to get your enthalpy of vaporization value. And this is something that we can do in our intro labs. So there's if we could do this, we can also just take that equation of a line and figure out a way to do this with just knowing what two of the points are, right? You need 2 points to make a line. Ideally, to get the kind of best version of this, you would take 2 points that are kind of on further ends of your data spectrum, right? Or range, sorry, your data range. And then what you can do is you can plug them into the Clausian-Clapeyron equation, which is a great and confusing name to say. But if you just have two measurements of a vapor pressure at a specific temperature and they're different temperatures, we can calculate that using this equation right here. And it's really just comparing two of these points on the line. So we'll have a pressure one and a temperature one, and a pressure two and a temperature two that we're using to calculate this. And that'll give us, we'll be able to solve for that enthalpy of vaporization. So let's walk through an example of this and show you what I mean. Cool, here we go. So here is this cyclohexane cyclohexene molecule, benzene, that instead of having hydrogens around, it has fluorines. And we have a lot of data for it. So we've got this temperature versus vapor pressure data right here. And so this would just be found in the lab, and you would just increase the temperature and read the pressure of the gas above the surface of the liquid. And this is in, sorry, the units are missing, millimeters of mercury for our pressure reading, which is the same as torr, right? So what we would do with this experimental data is we would then take our temperature values and compute what they would be as inverses. So 1 divided by the temperature. And then we would take the natural log of our pressures, and then we would plot our natural log of pressure versus our inverse of temperature. And we would get a slope that looks something like that, or a line that looks something like this. And we have data points, and so we'll fit a line to the data points that are coming from this table right here. And then we'll calculate the equation of that line. And so here's that equation of the line right here. Let's highlight it. And so what this is stating right here is that our slope value right here is about negative 288. So that slope value is going to be equal to the negative of our enthalpy or heat of vaporization divided by R. So solving for that heat of vaporization, we're really just multiplying this by -1, or multiplying this by negative 8.3145. And that's joules per mole Kelvin, which is going to give us an answer then that's going to be in terms of joules per mole. And so that value is going to be this number right here. This enthalpy of vaporization is 3.565 times 10 to the fourth joules per mole. And so that's how we could find this experimentally from that slope and then solve just from that. Now, if we didn't want to go through graphing, or maybe we didn't have this many data points, what we can always do then is plug into the Clausian-Clapeyron equation, and we should get something pretty close. So in this case, what we're going to do is we're going to take a couple of points, and I like to go at the opposite ends of the range to get a little bit more accurate. So we've got this one right here, where we've got at a temperature of 280 Kelvin, we have a vapor pressure of 32.4 millimeters of mercury. And then we'll also take the point at 340 Kelvin, that its vapor pressure is 483 millimeters of mercury. And so we're going to plug these into the equation here. Actually, let's change this color so it's easier to track. So our T1 is going to be the lower one right here. So that's the 280. And so our first pressure then too is P1, which will be on the bottom of our ratio for our pressures. And then our second data point is going to be T2, which is the first of the two in the temperature component of this equation. And then the numerator of our fraction of pressures. And so we'll take that natural log of those two pressures, and then we will divide that by this 1 minus T2 minus 1 over T1, and then multiply by negative R and get our enthalpy of vaporization that way. So then once we have everything plugged in here, really all we have to do is solve for this one variable. And granted, when we're solving equations that are this large, for just one of these variables, it's a lot of places to make simple math errors, but like with a strong background in algebra, this is a fairly straightforward problem then. And so we calculate enthalpy of vaporization, that's 3.56 times 10 to the fourth. So that matches nicely with what we found experimentally, finding the slope of the fitted line, which was 3.56534 times 10 to the fourth joules per mole. Not exactly the same, but pretty close, pretty good. Right. So there's another practice problem following this. Try it yourself first, and I'll walk through the solution.